we have all microstates are equally probable, okay, and we call this, what ensemble we call this? We call this the micro-canonical ensemble. And for that, we defined a macro state of such a system is defined by fixing the total energy, volume, and number of particles. And for a given macro state, there are certain number of microstates. This is number of microstates. For a given macro state. Then relation to thermodynamics is given by this Boltzmann relation in the S of EVN is equal to, there is a Boltzmann constant Kb, the logarithm of omega. So in some sense, this is the first relation in the equilibrium statistical mechanics that we have. Now, if you can remember that this equation is not derived. I even told you that there is no derivation. This is not derived from anything more fundamental. Now, suppose if our aim is to, so we have, let's say, we have some clue we have that omega is related to S. Okay, how do you have that clue is a different question, but let us start. We have to start somewhere. Let's say that we have some clue that omega is related to S. Then how do we come to this relation? Okay, so how do we come to this relation? So this is the question. Now you can come up with your arguments. Okay, so let me ask Abhinav. Abhinav, are you listening?
Hello, sir.
Yeah, Abhinav. So any suggestion? How do we come to this relation?
There was like something a relation between like entropies are getting added and omega is getting multiplied.
Okay, very good. So what Abhinav is saying is that suppose if I have a system 1 Okay, I have system 1, and then there is another system. Let's say system 2. These are two systems. Then let us say that omega 1 is the number of microstates of this, omega 2 is the number of microstates of this. Now S1 is the entropy, this S2 is the entropy of this. Now we know from thermodynamics, entropy is an extensive quantity. From thermodynamics, the total entropy of the system is S1 plus S2. Now, by definition, the total entropy, the total number of microstates is omega 1 into omega. So, we should have a relation such that the product of the argument will become sum of the functions. So, mathematically, I can say that I can formulate a mathematical equation such that saying, let's say S is equal to some function of omega. Okay, I don't know what this f is. Okay, S is equal to some function of omega. Then this f should satisfy a functional relation like this. F of omega 1 omega 2 is equal to f of omega 1 plus f of omega. So one can ask a question that what function will satisfy this kind of a functional relation. Okay, so this is one. So we have created a problem from our understanding that number of microstates is a multiplicative thing and entropy is an additive thing. If there is a relation between these two, that relation should satisfy this kind of a functional relation. So we can ask a question, okay, can we mathematically solve this functional equation and get the required functional relation between S and omega? Okay. So is there any other argument that you can think of? Akhil?
Yes, sir.
Yeah. So is there any other argument? Are you following this argument?
Yes.
Yeah. So is there anything else, or you think this is a good argument to start and
I
stop with?
I think this is good argument,
A
sir.
good argument. Okay. Atul Krishna, you have any additional argument?
No, so far I also thinking that it is good.
Okay. Okay. Very good. So is there anybody else who has a different argument to present? Okay. So if all of you are thinking that this is a good argument or it's an important argument, it is necessary that we should solve this problem, right? So the problem is find f such that f of omega 1 omega 2 is equal to f of omega 1 plus f of omega. I could have written it as f of xy equal to f of x plus f of y. So find f such that this is true. So this is a mathematical question. So how do you do that? Any idea? Avinash? Because yeah, so by inspection. So you can say that, okay, this is a very useful thing. So one can say that by inspection, that means we we scan all mathematical functions that we know of, right? So by inspection, you can say that logarithmic function is that satisfies this equation. So one is by inspection, and this is very important. Of course, most of the times we do many things by inspection, but there is no guarantee that whatever functions that we know will be a solution of this equation. There may be several functions that we may not know, and maybe there is some function which is not yet known to anybody, and you may have to create one. So there is that possibility, but inspection definitely is a valid method of looking for solutions in the first place. Okay, so at least we are, suppose if we did not know, let's say we didn't know this s equal to k log omega, is it easy to guess this by inspection? Now that we know it, we can say that, okay, that satisfies this. Suppose if we didn't know that, and let's say we don't also know a logarithmic function, then how do we get it? Because solving is something like that, right? So we have to solve this equation and get logarithm of omega as a solution of this equation. Jahang Pratap,
Yes, sir.
are you also happy with this inspection?
Uh, and not much, sir. It's because we know that we are able to guess. That's all.
Yeah, that's what I suspect, because we know it, we think it's not a big problem, but I mean, it's not a big question. But if we didn't know, then it could have been not that straightforward to guess it.
So we can check for the derivatives of the function. Then we can
You can
have
check
some
for
idea
what?
about derivatives.
So how do we do that?
Then from the slopes, we can have some idea how those functions slope. We can compare them both sides.
Yeah, but we don't know the function itself. Then how will we know the slope? See, this is slightly difficult task psychologically. We have to speak. Your voice is not audible. Also.
Are you able to hear me, sir?
I'm only able to make out that you're speaking, but I'm not able to hear what you're saying.
Okay. I think we should go for special cases like sigma 1 equal to 1.
Okay.
And then sigma 2 equal to 0, something like that.
You mean, are you saying that, can you write here?
I'll try, sir.
Yeah.
So the screen is stuck in the first phase, sir, in the screen sharing mode.
Screen sharing is what stuck in the first page.
Yes, sir.
Oh, I have to share every time I change the page, or what? Do you see now?
No, so last time it worked properly, sir. Maybe some network issue. Now it's fine, sir.
Ah, okay. So, are you all able to see what Arshad is writing?
Yes, sir.
Yes or no? Okay, that is, I think you will not get anything different. Both these equations will give you that f of 1 equal to 0. Correct? Arshad?
Okay, sir. So we know that it passes through 1, 0.
So, what I am saying is these two equations will simply tell you that f of 1 is equal. Correct? Do you get anything more than that?
That will tell us it cuts the x-axis at 1.
That tells you what?
It cuts the x-axis at 1.
Yes, okay. That tells you that it cuts the x-axis at 1. But I want function everywhere. So is this is definitely some information. There is no doubt about it. This is definitely some information. Okay, so one can try like this, but it's important to try because it is necessary that you should learn to take this functional equation and find a solution to this functional equation. Okay, so let me just tell you there is one standard method which
Sir,
standard,
sir,
yeah.
so we can take derivative with respect to omega 1 and then multiply with omega 2 of the and then take derivative with respect to omega 2 and multiply with omega 1
uh,
and then equate them because both are constants.
yeah,
Will,
that's right.
will that work,
So
sir?
okay, I think what you're suggesting is what probably is called the standard method, or the method which you can use to do this. So let us say that we will define this omega 1 multiplied by omega 2 as omega. Okay. So then what is our equation? Our equation is f of omega is equal to f of omega 1 plus f of omega 2. So let's say that first you differentiate this with respect to omega 1. F of omega is equal to this will be dou f by dou omega 1, and the derivative of this one is 0 because this is a function of omega 2. Now this left hand side you can write it as dou f by dou omega into dou omega by dou omega 1 by using chain rule, which is equal to dou f by dou omega 1. But what is dou omega by dou omega 1? That is omega 2. So from here I can write down dou f by dou omega is equal to, this is omega 2, right? So I will take it to the other side, 1 by omega 2 into dou f by dou omega 1. So let's call this as equation 1. Now I can do this same thing with take a derivative of this with respect to omega 2. That is dou by dou omega 2 of f of omega is equal to, first one will be 0 plus dou f by dou omega. So I can do the same thing, that is dou f by dou omega into dou omega by dou omega 2 is equal to dou f by dou omega. So this is nothing but dou f by dou omega is equal to, this will be omega 1. So 1 by omega 1 into dou f by dou omega 2. Now you can see this is, let's call this as equation 2. The left hand side of equation 1 and equation 2 are same. So right hand side should also be same. So now we can write down that 1 by omega 2 into dou f by dou omega 1 is equal to 1 by omega 1 into dou f by dou omega. So you take omega 1 this side, so omega 1 into dou f by dou omega 1 is equal to omega 2 into dou f by dou omega. So this side is completely a function of omega 1, this side is totally a function of omega 2. So this simply tells you, yes.
Stop. Screen is
What
stopped, sir.
happened? Huh?
This first screen is there only. I can't see the next page.
You are only seeing the second page.
Yes, sir.
Oh.
Sir, are you trying to share a single tab or window?
Window, yeah.
So you can try to share
I'm
the whole
sharing
screen.
within
In that case, I think it will not get struck.
Do you see some screen? What do you see now?
Sir, it's visible.
What do you see now?
It's third page. I can see it.
1 by omega 2.
Yes, yes.
So this tells you that you can write. So what I from equation 1 and 2 in the previous page. Now do you see previous page?
Yes, sir.
So if you look at this 1 and 2, the left hand side are same. So the right hand sides are equal. So I equated the right hand sides. And so I take omega 1 here and omega 2 here. So this is only a function of omega 1. This is only a function of omega 2. So that means you can write down for general omega into dou f by dou omega should be some constant. So this is simple. So if you integrate, then you get f is equal to some constant into logarithm of omega is equal to some constant into logarithm of omega, plus there can be some integration constant. So let's call that as some f naught or something. And now I can use the result which Arshad had shown, that f of 1 is equal to 0. Okay, so this result from the taking omega 1 equal to 1 and omega 2 equal to 1, Arshad had argued that this is equal to 0. So that implies that your f0 has to be equal to 0. The integration constant has to be equal to 0. So this function should be some constant, that is f of omega should be some constant, and we call that constant as kb. So this is a mathematical derivation or a mathematical solution of a functional equation satisfying the this relation like this. Yeah. So now you can ask the following question. For example, let's say that just for practice, let me just leave this exercise. Suppose I have a relation like this, that is f of x plus y is equal to f of x into f of y. Suppose I have a functional relation like this. Okay. So what kind of a function does this satisfy? So find f satisfying the above relation.
Sir, can we say that this equation is homomorphism because it's the image of the composition equal to the composition of the images. This is a homomorphism.
Which one? This?
F of x plus y
Uh-huh.
equal to f of x times f of y.
Hmm.
Is it a homomorphism? Because with respect to addition and multiplication, because it's a image of the composition is equals to composition of the images. F of
Yeah,
x
but
plus
the
y is the image.
composition here, the composition is with the two different binary operations, right?
Yes,
Here
sir.
I am composing x and y by adding them. There I am composing f and y by f and
Multiplying.
x and fy by multiplying. So it's not like homomorphism.
Sir, by mere observation, we can say that it is kind of exponential function.
Yes. So you are I think trying to do it by inspection, right? So by inspecting, you can guess that it is an exponent. If it is an exponential function, it will satisfy.
Yes, sir.
F of x is equal to e to the power x. Okay, but you can try solving it in this way and then get this as a solution. Okay, so that I will leave it for you to do it as an exercise. Now, I also wanted to just present another simpler argument. The argument in favor of S is equal to AB. Previous one was a mathematical argument. So let's present another argument in favor of this. So for that, let's consider two systems. So let's say this is system 1 and this is system 2. And these two systems are isolated from rest of the universe. Okay, so let's call this as system 1 and this as system 2. And this wall is such that the exchange of energy between these two systems is allowed. E can be exchanged. That means this is a what you call as a diathermal wall. It will allow energy to get exchanged, but it doesn't allow number of particles to exchange. And walls are rigid so that there is no change in volume. Only energy can be exchanged between these. Now this combined system is isolated. So if let's say E1 is the energy of this system and E2 is the energy of this system, then the total energy, which I call it as E0, E1 plus E2 is constant. There can be fluctuations in the energy of the systems, but total energy is constant. That means the composite system is isolated. So what happens is this E1 and E2, they keep changing, but then when equilibrium happens, equilibrium implies there is an average energy, which I will call it as E1 bar, and E0 minus E1 bar, that is E2 bar, are fixed. So average energy is fixed when you have a equilibrium situation. Now, how do we fix this equilibrium? For such system, E1 bar is such that the total omega, which is equal to omega 1 of E1 and omega 2 of E0 minus E1 is maximized. That means equilibrium corresponds to maximum number of microstates of this system. This is consistent with your postulate of equal a priori probabilities, because if all microstates are equally probable, the one with the maximum number of microstates correspond to the equilibrium. So we can ask a question that that means if you take del omega by del E1 and evaluate at E is equal to E1 bar, that should be equal to 0. Okay, this is the condition for the extremum, but for maximum also this condition should be satisfied. Now that implies what happens is I implement this derivative on the right hand side. So I have del omega 1 by del E1 into omega 2 of E0 minus E1. This entire thing is evaluated such that E1 is equal to E1 bar. This is a product, so I have to write down two terms plus omega 1 into E1 into del omega of E0 minus E1 divided by del E1, and of course this also is evaluated at E1 is equal to E1 bar. But this is basically E2. So E0 minus E1 bar is E2 bar. So I can write this as del omega 1 by del E1 evaluated at E1 is equal to E1 bar into omega 2 of E2 bar plus omega 1 of this course should be equal to 0. Omega 1 of E1 bar into omega 2 of E2 divided by del E2 into del E2 by del E1, which will be a minus 1 here. Okay, so this is equal to 0. Now you can see this implies we have so this minus sign, so I can take it to the other side, and then I bring this this omega 1 to this term and this omega 2 to this term. Then I will have 1 by omega 1 of E1 bar. Okay, so let me write down this E1 separately. Del omega 1 of E1 by del E1. All this is evaluated at E1 is equal to E1 bar is equal to 1 by omega 2 of E2 and del omega 2 of E2 divided by del E2, and all this is evaluated at E2 is equal to E2 bar. This is equal to this. So you can see once again, based on the logic that we just used, this is entirely a function of E1 and this entirely is a function of E2. So we can see that this implies you have 1 by omega of E into del omega of E by del E at equilibrium energy should be some constant. Or we can write this as dou by dou E of logarithm of omega of E is constant. Now look at this one, that this is some kind of a quantity of system 1, this is some kind of a quantity of system 2, and I don't know what this constant is. So let me call this constant as some beta. Okay, call it. So call it. So we don't know what beta is, but we know that it is some constant. So this constant is what I am now calling it as beta. Now let us look at physical picture. Okay, physical picture. Now what happens when energy exchange, and the energy exchange is allowed, when will this exchange when does a net exchange of energy is stopped? So if I ask this question, yeah,
So when the system will be in equilibrium,
system is in equilibrium. So what kind of equilibrium it is? That is, what property of the system 1 and system 2 should be same?
temperature.
Temperature. So physically we know that T1 should be equal to T2. So essentially we call this as a thermal equilibrium. Okay, when system reaches thermal equilibrium, there is no net exchange of energy in this system. Okay, so if this, like, there is some property of system 1 here and some property of system 2 here, this property should have some relation to temperature. So I'm arguing from this physical picture that this should be related to temperature, because temperature is one quantity which is constant when such an equilibrium takes place between these two systems. Now let's come to thermodynamics. Okay, so from thermodynamics, we can write down that there is a relation that 1 by T is equal to dou S dou. That means from here we get that it should be a constant. Then physical picture tells us that constant should have some relation to temperature. Then thermodynamics tells you that the temperature, inverse temperature 1 by T, is given by this dou S dou E. So now you can combine these three pictures and say that means if there is some quantity which is changing with energy, the rate of the change of that quantity with respect to energy, if that has to have a relation to temperature, thermodynamics is suggesting that the quantity that we should consider is the entropy. So from these two, we can conclude that is, from this and this fact, we can conclude that a change in entropy divided by some change in logarithm of omega. Okay, so that should be some constant. Okay, that should be some constant. So this tells you that your S should be equal to some constant AB times logarithm of omega. So this is another argument. Please don't understand any of these things as a derivation. These are not derivations. These are some kind of a plausibility arguments. We are trying to understand it, how this entropy and number of microstate connection can be justified from different points of view. So this is one argument where you can say that S equal to K log omega is a that is, this omega and S can be related, and the relation should be like this. Now you can also ask a question that if, for example, let's say that you have this total this omega, the total number of micros. I'm still continuing with this two systems case. So let's say that I have omega as a function. Let's call this, I write omega as a function of E1. Okay, omega will be a function of E1 comma E2. So I will say that it is E1 comma E0 minus E1. Okay. So this is total number of microstates of combined composite system. Now I want to so let us, I can write this as simply a function of omega of E1, right? This is E0 minus E1, the only variable is E1 here. Okay, so let E1 bar be the equilibrium value. Equilibrium value of E1. Okay. Now let us write E1 is equal to E1 bar minus some epsilon, where this epsilon 1 is very smaller. That is slight deviation from the equilibrium. Okay. Now you can show. Okay, so you can show that omega of epsilon 1 is a Gaussian. Okay, it's a Gaussian in epsilon 1 minus E1 bar whole square. Okay, so maybe let me put it this way: it's a Gaussian with mean at E1 and variance. Gaussian has a mean and variance, right? The variance is given by AB T square into C. Now I want you to do this. It's not difficult, but I don't want to do it here so that you get some practice. But I want you to recall a relation that we have derived when we did canonical ensemble. The relation that we have derived was, if you have fluctuations in E, the variance of the fluctuations are defined in this fashion. And we showed at that time that this is KT square C. So even when you take a small deviation from the equilibrium and then look at what happens to this omega, then it will be a Gaussian whose variance is exactly same as the variance that we have obtained in the canonical ensemble. So I want you to try this. So there are two exercises, I guess. So you have to do exactly along the same lines. Now what you do is you try to expand omega of epsilon 1 around E1 bar and retain terms up to quadratic in epsilon 1 minus E1 bar, and then neglect higher order terms and neglect higher order terms and then manipulate your derivatives, then you will be able to show this. Okay. So this is another interesting problem where you can see that the line of arguments that we have started with this can be continued and show that the variance are the fluctuations in the energy about the equilibrium flux. These are called equilibrium fluctuations. So equilibrium fluctuations are related to the specific heat of the system. Okay. So I think we started with a question that is Boltzmann relation, and we wanted to understand from the Boltzmann relation how this relation is obtained in the first place. Then we have a mathematical problem that it should have a functional relation like this, and this functional relation is what gives rise to a functional relation. So I have one method where I do a differentiation with respect to omega 1 first, and differentiation with respect to omega 2 next, and then from those two equations I will get an equation like this. This means a property called omega into derivative of f with respect to omega is constant. So that if I solve, I will get it is a constant times logarithm of omega plus f naught. But you can argue from the equation that f of 1 is equal to 0, and hence f naught is equal to 0. So you have f of omega is equal to kb logarithm. This is as a direct solution of this functional relation. So I told you that you have I gave another functional relation, and it was easy to guess that it should be exponential x, but you proceed in the same way to get this as a solution of this equation. Now I have presented another argument in favor of understanding this S equal to kb log omega, where I took two systems which allows energy to be exchanged between them, and the total number of microstates is multiplication of the number of microstates of individual system. Now the combined system is an isolated system, so equilibration occurs when the total number of microstates is maximized, and that maximization leads to a condition like this, that you have 1 by omega into the omega dou e, or dou by dou e of logarithm of omega is constant. Then I have compared this physical picture. The two systems are equilibrated only when energy is exchanged, only when their temperatures are becoming equal. So this constant should have a relation to temperature. And from thermodynamics, we know that the variation of entropy with respect to energy is what gives you the temperature. So that gives us that there should be a relation between entropy and logarithm of microstates, and that is another argument which tells us that there is a this is plausible, that S equal to k log omega is physically a possible. Then I said that okay, if you the total number of microstates, if you just deviate a little bit from the equilibrium, there will be fluctuations, and the fluctuations can be shown that it is equal to kBT square into CV. So this exercise is something which I left it for you to try. Okay. So now, so I think this part of discussion on S equal to k log omega is done. So now we can okay. So now the second important aspect of statistical mechanics, I think the next important. So S equal to k log omega is basically the equation of microcanonical ensemble, where the entropy and these things are related. Now, in canonical ensemble, we have derived that in canonical ensemble, we what is the entropy? We have entropy S is equal to minus AB into sum over I Pi logarithm of Pi. This is what is called the Gibbs entropy relation. Gibbs entropy. We have shown this earlier. Now, if you choose, if Pi is chosen as 1 over omega, that means equal probabilities. Equal probabilities. To all microstates. Equal probabilities to all microstates. Then you can show that, substitute this, then you get back here S equal to KB logarithm. This also we have shown earlier. Now, what I am trying to say is that suppose if I have this, okay, so let's say that this is the entropy relation. Okay. Now, these PIs have certain constraints. Okay. What are the constraints that these PIs have? Let's say that sum over I Pi should be equal to 1. This is basic constraint because okay, let me also remind you what is this Pi. Pi is what? Pi is probability of ith microstate. Probability of ith microstate. Okay, so this is your Pi, and so the total probability should be equal to 1. This is definitely one constraint. Now, if the energy is exchanged, then you have each microstate may have an energy epsilon I. Then you can have a constraint that Pi into epsilon I, Pi into epsilon I should be equal to the average energy of the system. Okay, so the average energy of the system is given by the internal energy U. Okay, so this is called average energy. This is our second constraint. Okay, and there can be another constraint, that is, let's say that if each one of these microstates has got certain number of particles, that means if the number of particles are also being varied, then you can have a situation sum over I Pi Ni, number of particles, should be equal to average number of particles. This can be written as average energy. So this can be a third equation. Now, the interesting problem is the following. Suppose if you ask a question that find the set Pi star that maximize S is equal to minus KB sum over I Pi logarithm of Pi subject to constraint 1, only subject to constraint 1. Okay, in that case you will get Pi is equal to constant. What is that? This is your microcanonical ensemble. That is, total probability should be 1. There is no other constraint. So if you maximize this with respect to this constraint 1, then you will get microcanonical ensemble. On the other hand, subject to constraints 1 and 2. Okay, that is average energy constraint and total probability constraint. Then we get Pi is is proportional to e to the power minus beta A. Okay, so this is your canonical ensemble. Now, if you subject this maximization to constraints 1, 2, and 3, then we get the probability to be proportional to e to the minus beta of epsilon I minus mu times. So this is what you have a grand canonical ensemble. So the three ensembles that we have discussed, their probabilities can be obtained by maximizing Gibbs entropy with respect to different constraints. So how do you do this maximization? We use this Lagrange multipliers. Okay, the technique is use Lagrange undetermined multipliers. Is equal to 0. Lagrange multiplier. And you have to set up these equations for all I is equal to 1 to n and solve these n equations to get a point which extremizes this function. Okay, so it's not very difficult. So let me just do the first one. So I have S is equal to, that is, I have a S of P1, P2, over I, pi log pi. This is the function to be extremized. And the constraint is that sum over I pi minus 1 is equal to 0. This is the constraint equation. So that means I have, let's say, j into kb sum over I pi log pi minus some lambda Lagrange multiplier into dou by dou pj of sum over I pi minus 1 is equal to 0. So this is your f. So this is your f, and this is your g, the constraint equation. So that is can be written in this following fashion. So minus kb sum over I. So I have to use a product rule. So dou pi by dou pj will be delta ij. Delta ij logarithm of pi plus this will be 1 by pi. Pi will get cancelled, and then you have a delta ij minus lambda times sum over I delta I is equal to. Now this delta ij means in this summation only I equal to j term will remain, all other terms will become 0. So minus kb logarithm of pj plus 1 minus lambda is equal to 0. Okay, so this implies I have kb logarithm of pj plus 1 is equal to minus lambda. Okay, or in other words, logarithm of pj is equal to minus lambda minus 1 divided by k. So you can write down this pj is equal to e to the power minus lambda plus 1 divided by. This is anyway a constant, and so now you ask a question that uh, so uh, so to obtain lambda, we set we use constraint equation. Obtain constraint equation, and what is the constraint equation? Sum over j pj is equal to 1. That means e to the minus lambda plus 1 by kb into, this is the same, right? So sum over j into 1, and this simply tells you whatever is the number of microstates, that is this. So this should be equal to 1. Now the number of microstates is, let's say, omega. So e to the minus lambda plus 1 by kb into omega is equal to 1. This implies e to the minus lambda plus 1 by kb is equal to 1 by omega. So this tells you that your pj is equal to 1 by omega. And this is what is the probability for, this is for the microcanonical answer. Now you can see that I can, so if you use, for example, total probability constraint and the average energy constraint, then you will get that we have done it in a different form earlier. In the most probable this thing, it is exactly same. You have to use two Lagrange multipliers because there are two constraints. One is total probability constraint, the other is average energy constraint. So in that case, you can show the canonical probability distribution, the probability for a canonical ensemble. So maybe that CE and GCE, I will leave it as an exercise. I think you can try that. Okay, so by simply extremizing this Gibbs entropy with respect to the respective constraints and trying to determine these coefficients by using the equations of constraint. Okay, so this is another way in which we can see that all these ensembles can be obtained by extremizing entropy subject to different constraints. Because this in the first case energy is constant, in the second case energy is not constant, so we have to use an average energy constant. In the third case, even the number is not constant, so we have to use average constant. Okay, so this is another set of problems which one can try and visualize that the different types of ensembles has the consequence of maximizing the entropy with different conditions. Any questions?
Sir. Sir. Hello.
Why there are only less than 10 people who are able to join this Jamboard? Others have a difficulty with memory or something? I think there are 74 people there, but you won't be able to join in the Jamboard. Is it heavy on the memory if you join?
Sir,
Yeah.
so did you wrote anything on page 6? It is blank there.
Yeah, it looks like it is blank. I think I didn't write anything. I don't know if there is a way to cut that. Okay, I think it was just blank. Somehow it was blank.
Sir.
So is there Is there something that you
Sir, can you explain that argument in page 5 again?
argument on page 5?
Yes, sir.
So up to what?
Sir, between this
with this
del by
part?
del E of ln omega and this 1 by T del S by del E. How are you going to that delta S by delta ln W, ln omega?
Because 1 by omega del omega by del E can be written like this. That is clear, right?
What, sir?
So from here to here it is clear.
Yes, sir.
1 by omega del omega by del E can be written as del log omega by del E. That is clear, right?
Yes, sir.
So in the physical picture, temperature should be equal. That is also clear. This argument is clear. Now in
Yes, sir.
thermodynamics, we have a definition for the temperature like this. So you can ask a question, change in which property with respect to energy is temperature. So suppose if you ask this question, change in which property with respect to energy is temperature, then thermodynamic gives you an answer, entropy. Okay. So here, change in some property with respect to energy is related to constant. That should be related to temperature. Okay. And all these arguments combining, we can say that if there is a change in delta, if change in S, there should be a change in logarithm of omega. Okay. So I am trying to combine all these arguments and then come to a conclusion that such a relation is a plausible relation. So is there any particular difficulty with respect to solving problems in this subject? Have you tried to solve problems in the first place?
Sir, hello?
Yes. Yeah.
Sir, so I didn't understand the part why f of x plus y equal to fx times fy is not a homomorphism. Uh, the question I asked, you said that both the binary compositions are different, but if they are different, we have two different groups. Like one is G positive, G addition, and G prime multiplication. Then if we define a mapping from G to G prime, then it should be homomorphism. No? If G
See
and G
here,
hello?
this is just a functional relation. Okay, so how do you define a homomorphism? Homomorphism is a function from one group to other group, right?
Yes, sir.
Right. So that means it should satisfy the what is called the group multiplication table. Okay, but I don't even want to have a group structure here. Okay, so whatever I am writing here, I don't even want it to be a group structure.
No, sir,
It
if we
is
have
just a
like R
functional relation
plus,
between this.
like R is a real line,
Uh,
R plus and R multiplication,
uh,
then the two groups are different.
mm,
Then a mapping from R plus to R multiplication, that if that satisfies f of x plus y equal to fx times fy, then it should be homomorphism. No? If two groups are the same, then it's a endomorphism. Hello? Sir?
yeah, but I don't know if, for example, if you take R with multiplication, uh, then, for example, 0 doesn't have an inverse, right?
Yes, sir, but 0 is excluded. Because
So I
0
don't
doesn't
even
have
know
multiplicative inverse, 0 is excluded.
excluded.
For every
So if you are saying that you have R plus with multiplication, this is okay. This is a group because you have inverse, everything is there. But R plus and plus, uh, this is not a group because in the R plus the inverses are not there. For that you have to take the full real line. There is a real line with plus is a group, and the R plus dot is a group. Okay, that's fine. Then you want to have a function from here to here.
sir, sir, I think R dot is also a group. 0 is excluded.
So that means it should be R minus 0 dot. So you are saying this is a group.
Yes, sir. Yes, so when we consider a ring, then we also write R plus dot is a ring. We exclude 0 for, in terms of multiplying. When we consider
Yeah.
R plus dot is a ring,
Okay, so let's say, yeah. So so let me say that it. Okay, are you getting an additional advantage by having realized that this forms a homomorphism or not forming a homomorphism
no,
and
so it
getting
was
the
just a
solution?
curiosity because the structure looks similar. So, does it have any?
Okay, okay. Yeah, it doesn't seem to help us in any way here, to my knowledge at this moment. But yeah, there seems to be a structure like
Okay, sir. Thank you.
that. Okay, so that is now another set of problems that we. So, like I told you in the last class, we have also looked at, for example, let's say that you have energy En is equal to some n times some epsilon. So epsilon is some positive constant, positive constant. And you have n epsilon, that is epsilon n is equal to n epsilon. So these are energy levels of then how do you calculate the partition function? Z is given by And of course, your n will start from 0, 1, 2, etc. So z is given by sum over n is equal to 0 to infinity e to the power minus beta n epsilon. So which is like you write it as n is equal to 0 to infinity e to the power minus beta epsilon raised to the power n. Now e to the minus beta epsilon, the modulus of this value is less than 1, and therefore you can write down this partition function using a geometric series. The sum of the geometric series will converge to a function like this, e to the minus beta epsilon. This is something which we have seen in Einstein model, and so I'm not doing anything different here. Instead of writing, for example, in Einstein Planck's model, we call epsilon as h nu. That's the only difference, right? So here I'm calling this as this is in Planck's model. Now, suppose if I say that, so now let's look at a different problem. That suppose I have epsilon n is equal to n epsilon, and each epsilon n is n-fold degenerate. N-fold degenerate. That means I have epsilon n, that is, let's say this is the ground state, first excited state, epsilon 0, and first excited state. Second excited state is 2, third excited state is 3, and so on. Okay, so like that. So what kind of partition function do we have here? So we can have, so if you write down this one, I write down n is equal to 0 to infinity. So I will have, okay, so let me write down the first one. The first one is 1 e to the minus beta epsilon 1 plus 2 times e to the minus beta epsilon 1 is simply epsilon, 2 times epsilon plus 3 into e to the minus beta 3 times epsilon, and so on, plus n into e to the minus beta n times epsilon, and so on. So what kind of a closed form expression this one will have? Lucinder?
Yes, sir.
Any suggestion?
I think you can add an weight factor to each term that accounts for that degenerate.
What will be the closed form expression? So what I have is say z is equal to 1 plus e to the minus beta e plus So this equation is like you have a series which is like 1 plus x plus 2x square plus 3x cube plus etc. plus n x to the power n and so on, right? So I want kind of a sum of this kind of a solution. So we will see that suppose if I take let's say let some s naught is equal to 1 plus x square plus etc. This we know is equal to 1 by 1 minus x, correct? So I am trying to just tell you that we can actually do some manipulation. Suppose if I write what is ds naught by dx, that is equal to 1 plus 2x plus 3x square and so on, right? So if I multiply this one with x, ds naught by dx, if I write, it will be x plus 2x square plus 3x cube, etc. And what is this equal to? This is equal to s minus 1, because this 1 is taken this side, minus 1 is equal to this remaining, and this remaining thing is given by this x into ds naught by dx. So what will be your s? S is equal to 1 plus x into d by dx of 1 by 1 minus. So that is equal to 1 plus x. You have minus 1 by 1 minus x whole square into minus 1. Okay. So that will give you this minus 1 and this minus 1 will become plus 1. So you have s is equal to 1 plus x divided by 1 minus x the whole square.
Sir, we can do another method by another method. I did it with another method, sir.
Yeah,
Sir, 1 plus x
yeah.
plus
What is
2x
that
square
method?
plus 3x cube. We write 1 plus, we take x common. We pull out x, then we get within bracket 1 plus 2x plus 3x square. And that is 1 minus x to the power minus 2 by binomial expansion. One,
Yeah.
sir, actually 1 plus, we take x, we pull out x. So we take 1 plus 2x plus 3x square.
Yeah, 1 plus. So you are saying at this point you write it as 1 plus x into 1 plus 2x
Yes,
plus
sir.
3x square, like that.
Yes, sir. Then that is
Then this will be
1 over 1 minus x square. Within the bracket,
yeah.
the
So you are
sum within the bracket.
yeah. So that means this is 1 by 1 minus x the square.
Yes, sir. That is the
Okay,
same
so that's
answer.
what I same answer. But if you remember that binomial expansion, that is fine. You can use that. But whatever I have done is that I am assuming that, of course, I don't remember most of the things, so I always try to get this from some trick like this. Okay, so this is what it is. So what is our x? X is basically e to the minus beta epsilon. So our partition function is 1 plus e to the minus beta epsilon divided by 1 minus sigma minus beta epsilon square. Yeah, so that is so this you can write it as, I think, this is 1 minus 2x plus x square plus x divided by 1 minus x whole square, that is equal to 1 plus x square minus x divided by 1 minus x. Whatever it is, this is some kind of a form for the partition. So what I'm trying to tell is that when you have this kind of degeneracy, different types of degeneracies, then you should manipulate with the known function and try to see by taking the derivative of this one, you can get okay. Now I just wanted to tell you that these quantities, this omega and z, these things that we are calculating, they are, I mean, their numerical value is huge. I'm using this word huge because it is not large, it is huge. Because when you say you have number of particles, it is of the order of 10 power 25. This itself we called it as very large. Okay. But this is very huge compared to whatever very large that we are talking here. Okay, so for example, there is a problem like this. Suppose if you say that let's say we have a photon. Let's say you have some kind of a yellow photon. Okay, that means let's take lambda to be some 500 nanometers. Okay, so let's say you have a yellow photon is absorbed by some macroscopic system, by some system. Now we would like, because of this absorption, there were certain number of microstates of the system initially, and because of this absorption, this number of microstates will go from omega I to omega f. So we can ask a question: what will be the increase in the number of microstates? So you can see that the change in entropy of the system, let's say this whole thing is happening at room temperature. Let's say at T is equal to, let's say, 300 Kelvin. Okay, so T times delta S is your delta E, which is equal to T times delta S is delta A, which is equal to H nu. That is equal to Hc by lambda. Okay, so now you can ask what is delta S. Delta S is equal to Hc by lambda into T. Hc by lambda into T. So you substitute this Planck's constant. Okay, H is roughly some 6 into 10 to the minus 34. This is some 3 into 10 power 8 meters per second, and this is 500 into 10 to the minus 9 into 300 Kelvin. So you can see that this 6 into 3 and 5 into 3, we can assume they will go. There is a 2 here, 4, so this is 10 to the minus 5. So this whole thing, when it comes, it will become 10 to the 5, the numerator. So 8, 5 is 13, and 34, 13 is like minus 21, right? So this is of the order of 10 to the minus 21. So this will be so many joules per Kelvin. That is what your change in entropy. But you know that this change in entropy can be written as Kb into logarithm of omega f by omega I. Omega f by omega I. So if you want to find out what is logarithm of omega final by omega initial, then you can write this as whatever delta s divided by A. And delta S is roughly 10 to the minus 21 joules per Kelvin, and this is 1.38 into 10 to the minus 23 joules per Kelvin. So this is 100. Okay, so you can see that this omega f by omega I is of the order of e to the power 100. Okay, so that is roughly 10 to the power 41 or something like that. So your omega f, we don't know what was omega e, but whatever was omega I, it is multiplied by 10 to the 41 times that of that. Remember, just a tiny photon is absorbed. This is the huge increase in the number of microstates that that you have for the system. So this number of microstates is a very huge number, considering. So another way to understand this is that is if your n is of the order of 10 to the 25, okay, and this omega is of the order of 10 to the 10 to the 25. Okay, so this is the kind of order in which this omegas will be there. So this, if you call this as large, and this is, I don't know, these are just English words that we use for large and huge, but the difference between these numbers are really something which is mind blowing, in the sense this itself you consider to be very large, and these states are really huge number of states. So there is no there is nothing saying that I have omega and omega plus 1 or omega plus 10 to the 24. Omega plus 10 to the 24 is also a meaningless quantity to talk about, because when it is 10 to the 10 to the 25 is the number of microstates that we are going to consider. So pay respect to these numbers, because that is why logarithm is so important. If you take logarithm of omega, at least it will be of the order of number of particles. Okay, so that is another point which I wanted to make, so that you get a feel for the numbers. Okay, so I will close here, and if there are some questions.
Sir,
Yeah.
so will you explain
Yeah.
the absorption of a photon by a system and the increase in the number of microstates? How does it we can understand physically?
Basically, system gets heated up for any absorption of energy, and entropy will increase, right? So if there is an increase in energy, and increase in energy will give rise to increase in thermal energy, which will give rise to increase in entropy. And increase in entropy is related to the change in the number of microstates because of this direct relation between entropy and number of microstates.
So due to increased energy, the system has larger number of possibilities in existing.
Correct.
Okay, thank you.
Sir, how did you take that expression omega f by omega I?
That expression is, S equal to K log omega. So initial entropy is Kb log omega I. Final expression is K log omega F. So SF minus Si is the change in entropy.
Okay.
That is K log omega F